Well, good afternoon, everyone. I'm Bob Altenkirk, the 7th president of NJIT. Let me welcome you to the presentation of the NJIT Overseers Excellence in Research Prize and Medal for 2011. This year, in addition to the individuals on campus, I'd like to welcome all of those of you who are with us on the internet. We're also recording today's ceremony so that it can be viewed later on the NJIT website. As we begin, I'd like to especially acknowledge Phil Rinaldi, who's sitting here in the front row on my left. Phil is an NJIT graduate. He's a longtime friend of the university. He became an overseer in 2000. Recently, Phil was elected chairman of the board, succeeding Emil Herkert. As I'm sure many of you know, Emil enthusiastically and energetically advocated establishing this award that will be conferred today. I'm also glad to see our audience here in this historic building that we renovated a few years ago. Our audience includes distinguished university leaders, among them Dr. Joel Bloom. Joel, who newly appointed interim president of NJIT. Let's see, from the Board of Overseers, from the Board of Trustees, Vince DiCaprio. Vince in the second row there. And it's my pleasure to acknowledge all the members of the Board of Overseers. If all of you would stand up, we'd recognize you. We also have some Overseers College Research Award winners. I saw Dale Gary, Dale from the College of Science and Liberal Arts. And I think that's all for the moment. We may have some others coming shortly. At this time, I'd like to acknowledge the attending members of the committee that had the challenging task of selecting the recipient this year of the Overseers Excellence in Research Award. Committee's chair is Emil Herkert, Erwin Doros, Provost Ian Gatley, J. Robert Hillier, Vince Namoli, Phil Rinaldi, and Don Sebastian. So this afternoon, we're going to honor Dr. Haim Grebel, a member of the Department of Electrical and Computer Engineering. As you'll hear, Haim's research is in the realm of the incredibly small, but it has very large real-world applications. So it's now my pleasure to introduce Don Sebastian, NJIT Senior Vice President for Research and Development. And Don's going to tell you more about Haim's accomplishments and introduce a video that was produced for this year's award ceremony. Don?
Thank you, Bob. The Overseers Research Medal was created by the Foundation in 2008 to give visibility to the breadth and depth of research at NJIT. Our faculty interests truly range from understanding the cosmos to characterizing the structure of the atom, but always with an eye towards harnessing knowledge to accomplish practical goals. The 1966 movie Fantastic Voyage imagined a future where man could experience and manipulate world at molecular dimensions. That was science fiction. Our honoree today is a true modern micronaut who not only sees molecules, even atoms, but can also manipulate them with surgical precision to build functional structures, forming the basis of new sensors, digital computing, imaging, and medical diagnostic equipment. We refer to operating at the edge of knowledge, and that is precisely this interface between leading-edge science and practical application of which we speak. Dr. Grebel has been integral to the growth of NJIT as a doctoral research university. For over 25 years, he served as a member of the Newark College of Engineering's Department of Electrical and Computer Engineering. He's director of NJIT's Electronic Imaging Center and a member of the Interdisciplinary Program of Materials Science and Engineering. And it is so often the case, our best researchers are also our best teachers. Haim is beloved by his students, and respected by his colleagues in and outside of NJIT. His selection by his peers in 2009 as the Newark College of Engineering winner of the Overseers College of Engineering Research Award made him a candidate for the award that we bestow today. They say a picture is worth 1,000 words, so a video should be worth almost 2 million words per minute. So why don't we use the technology to tell Haim's story a little bit more compactly than reading a 10 million word tome, but with no loss of content.
In order to be a great researcher, which is what we're honoring Dr. Grebel for, you have to have that spark. You have to have that human spirit of discovery.
With Dr. Grebel, life is just research. Every breathing moment for him is research.
Dr. Grebel is a brilliant researcher, and he's also someone who cares about the people he works with.
My name is Haim Grebel. I'm a professor of electrical and computer engineering at NJIT. I'm also a director of the Electronic Imaging Center, and my passion is nanotechnology. My father was an artist, and he used to say that art is creating new things. Science, in essence, is the same thing. You create new things, new structures, new materials. What we do here is growing carbon nanotubes. Carbon nanotubes is a rolled graphene. When you take graphene and you roll it into a tube, like very thin wires. That means that we can build up very small circuit with carbon. And since carbon is biocompatible, which means the body does not reject it, then you can think of way of functionalizing carbon nanotube to aid public health. What vision do we have for those small circuitry? How about a small circuit in the brain to combat Alzheimer's disease? Nanotechnology is not just about small stuff, it's about innovative nanostructures. Here at NJIT, we can devise carbon-based films which prevent corrosion of prosthetic limbs. Yet another example, we use graphene to devise special platforms which mimic the way viruses attach to membranes of our body, either swine flu or avian flu. And by detecting the attachment or the binding process, one day, hopefully we'll be able to devise better drugs to combat those viruses. We're not just growing carbon nanotubes or graphene, or not only functionalize them, we need to characterize them. That means that we use lasers, we bounce the laser off those structures, and we look at changes of these laser beams. This gives us an ability to see, quote unquote, what we have fabricated and assess how effective or ineffective these structures are.
What is the old saying, right? Man is the measure of all things, so we have to bring these other dimensions to the research. That's the best way to describe his body of knowledge. It was just inspired, really.
The best work comes from people that are really happy about and passionate about what they're doing. He's very good at keying in on individuals' interests and talents.
He inspired me to read voraciously and come up with my own ideas. There's always something new to do, there's always something new to try.
His discipline to pursue a technical problem, it was a big influence, and it really helped me in the pursuit of finishing the doctoral degree.
To me, teaching is addressing students as future peers, that I just share my experience with them and they share their experience with me.
As an undergraduate, Dr. Grebel gave me the opportunity to participate in something real life. He really wanted us to make a contribution to his department.
It's not just the research students who are working day and night. He worked with us day and night too.
He was very much a mentor in that way and a leader.
As a teacher, I'm bringing the same passion that I had at NJIT working with Dr. Grebel. I hope to inspire my students to consider science as their future.
Research is not just solving problems that we face now. It's not just about the number of papers, it's about the quality of work, it's about the quality of life, that you want to make an impact on other people's life. It's also about asking the right question that future generations will be able to solve.
I didn't even have to ask. I was going to say, I'm quite sure that I know that Haim, as a modest person, more modest perhaps even than, or as modest as his accomplishments as a scientist, is probably embarrassed by all this fuss. But I would say in his debut as a video star, along with all the other colleagues, they did a wonderful job, and I was going to ask for your applause, and I'll ask again because it was so good. Haim will be up in just a bit to do what he's really comfortable about, which is to talk about his science and his work. But before we get to that part of the program, it's my pleasure to introduce the chair of our overseers, Phil Rinaldi, who would like to make a few remarks on behalf of the board. Phil?
Thank you, Don. Thank you, everyone, for being here to help support this fantastic award to a fantastic researcher. We are shortly going to present a distinguished scientist with an award that honors Haim Grebel and, in its own way, is a tribute to NJIT and our ability to go ahead and generate world-class research. I'm a graduate of NJIT, and I'm very proud to be here and be part of this terrific ceremony. The support of all of our governing and advisory boards since the founding of NJIT has been important for our community, for the development of this university. And nothing is more important than the research that is being done. My predecessor as chair, Emil Herkert, was particularly instrumental in creating this award, and this was an award to both recognize the great talent here on the university and to also, frankly, allow the university to trumpet itself to the greater environment. So with these exceptional achievements, it's now time to present this award. Dr. Grebel, Dr. Altenkirk, if you'd please come up. So Dr. Grebel, podium is yours.
Well, I'm out of words, so I prepared the thank you, which is proper here. Well, to the Board of Overseers, a selection committee, the chair, Emil Herkart, Irvin Doris, the provost, Ian Gatley, Robert Hillier, Vincent Nemoli, Philip Rinaldi, the present chair, Senior Vice President for Research and Development, Don Sebastian, to Sunil Sehgal, the Dean of Newark College of Engineering, Stu, who worked on my nomination, to colleagues, to students, friends, and family. Really, thank you all. I'm really humbled. Beyond the mere recognition of past and present achievements, I believe that the board has sent a message here, and I would like to share it with you, because nanotechnology is about interdisciplinary activity. And I think that the messages of working together for both research and education is a good one. It's a good one to carry it out, and certainly to carry it out on nano stuff. And I couldn't have gone without students, postdocs and graduate students, undergraduate students, even high school. Least of all is my son, who was here and working here for 2 years. Well, what is nano? And I'll try to explain it to you for, I think I have only 15 minutes after such a long thank you. So there's a lot of commotion about nanotechnology, and the objective is to study and realize unique nanostructure which are important for electronics, optoelectronics, chemical and biological system. And the hope is maybe one day to have a nano machine to clean our arteries. And the hype is that everything's going to be fine once we have clearing out some few hurdles. So what is the future? Well, frankly, my dear, it's not plastic anymore. It is nano. So many aspects in our lives are related to phenomena at the nanoscale: DNA, colloids, clusters, laser toners, clay and cement. And it's not just that we work on it to understand what the features are, but we want to structure and restructure other things, some new things that are not even existing. Drugs which target specific tumors, nanocircuits to combat Alzheimer, energy harvest suits, or maybe to stitch out nerve cells. We need to dream. And I felt appropriate to quote my dad, who was an artist, that in my humble opinion, the artist has to possess an extra vision. It is not just enough for the artist to see reality as it is. With the power of his superior vision, the artist needs to control or relate to technical means of design. This he to learn throughout his life. For the creations that are emerging from the hands of the artist are but a story in installments, and the process of creation itself is a story without an end. And all you have to do is replace the word artist with a scientist, and I think that you got, or a teacher, and you got the story, the full story. So what is nanotechnology? I promised Phil to explain that in simple terms. So maybe shorty was an attitude, tiny was an oomph, really small. Very small indeed with an added value. Well, the last one is the one that I want to dwell on. But the question is usually, how small is small? So imagine Snoopy with his full hair skull, or mine, for example. And you think, and usually a hair is about 100 micron large, or in diameter of 100 microns, and you consider 100,000 times smaller than Snoopy hair. So let's say Snoopy hair is the giant jet stadium. So take the giant jet stadium and point out to one person out of that crowd. That's about 100,000 times smaller than something. So 100,000 times smaller than Snoopy hair is nanoscale. But is it just about small things? So I just brought an example of an ordinary mirror. We look ourselves in the mirror, hopefully once a day, once a week, maybe once a year. There are some other wishing mirrors. Little meow wants to be big meow. But the Romans, many years ago, found out that if you embed nanodust of gold or silver in their glasses, you see funny colors. In this case, in the British Museum, you see green in reflection and red in transmission. And so E&M 101 for you, large mirror reflects more or less colors equally, and yet when the particle becomes smaller and smaller, they reflect special color other than others. In this case, the green, and that green is missing from the transmitted spectra, and so you see red. Red and green are complementary colors. And this idea is used for stained glass all over the world. So other attributes than just beauty in the eyes, and research has demonstrated that better optical interrogation is made when the molecules are interfaced with metal colloids. The problem is that when the metal is interfaced with the bio species, sometimes you impede the signal and you don't enhance it. So we took a different approach, and here is a commercial system whereby a molecule is attached to a receptor. The receptor is embedded on a metal film, and while the molecule is attached to the receptor, something happens to the incident light. So in order to see what we're doing, let me take you some few hundred years backward. And this is about graphite, which has been known by the Aztecs and later on in Germany and later on in England. And some people say that black market is named after the illegal stolen good market of graphite. But seriously, graphite is in our pencils, something that we've used in elementary school. And the difference in the hardness of pencil is just how much clay you put in. So graphite is there, so it used to be mistook for pencil, for lead. That's why we call it lead pencil, actually. But it is graphite nonetheless. And so what difference is the graphite there than the graphite we use? Well, to understand it on atomic scale, graphite is a layered system, and graphene is just one layer, one atom thick of that graphite. So the big deal is how do you make it and how do you lay it out? And what we want is to lay it out on something which looks like a Swiss cheese in metal. And the reason why we want to do that is because this Swiss cheese in metal has funny things that light is tend to concentrate in the opening of that Swiss cheese. So if you're going to put a molecule, say biomolecule, inside that hole, it's going to fall through, so you need a trampoline to hold it back. And this is what the graphene does. The graphene is also good because it's biocompatible. But we want to mimic real biological interactions, so we put a membrane, and that membrane is a building block of most living thing. It's a lipid membrane. And so we put the receptors that I introduced before inside that membrane, which is on this graphene, which is on this Swiss cheese metal screen. Is the picture clear? So here it is in motion. And I show an example where the receptor is simply biotin. Biotin is B12, the one that we take for our diet, and we use for our diets. And streptavidin is just an example of a polymer that attaches itself very strongly to streptavidin, to biotin. And what we saw is that if you put the streptavidin strictly on some substrate, the signal is not so large. What we measure is the absorption of that streptavidin. But if you put it on the screen, those absorption lines are largely accentuated. So how about if we put it or use the same idea for flu viruses? So here's the screen, the membrane in it, the membrane on it. You put the receptor in the membrane, the lipid membrane. And then the idea is that if the flu virus attaches well to the receptor, this is the lower swirly picture, like a lock and key, then you will get a large signal. Whereas if you don't have a large interaction, say human receptor and avian flu, then they are basically detached and we won't see any signal. And indeed, the infrared spectra of avian flu, which is attached to its receptor, shown in the red, you see those few bumps in the spectra, which indicates strong binding, where if you don't have a binding, it's flat as is. And same with the swine flu virus. So what's the message? The message is that we have established a fast and sensitive technique, which could be available at point-of-care facilities. Simply swipe your saliva on this magic platform, and voila, you can distinguish between a common cold and swine flu. And this is very important because pandemic is one of the issue of pandemics to distinguish the good from the bad. So is this all what we can do with nano? Well, not quite. Carbon nanotube, which I think I brought one with me, it's on stuff on that platform, is maybe described as raw graphene. Basically, graphene, as you could understand so far, it's like a piece of paper that you fold off into a tube. And the tube is very narrow in size, 1 nanometer in diameter. So what do you do with this? So how about some circuitry? And the question here is, how do you grow this specifically between two electrodes? So we've been able to do that with the help of Bell Labs. And on the right lower screen, you can see the strand of 1 carbon nanotube between 2 electrodes, which we're very proud of because we hold the world records of yield. It's about 60%. The competitors are sort of 1 or 2% behind. So why is that important? Because one of the triumphs of quantum mechanics was the invention of a transistor. So what is a transistor? Well, a transistor is a channel, in this particular case of transistors, called field effect transistor. And the channel, this is the zigzag tube between the 2 blue electrodes on top of the silica, is funneling an electron, and a third electrode at the bottom of the silicon is sort of controlling how the flow is. is going to be made. And demand dictates smaller and smaller transistors for faster and smaller circuitry, cell phone, tablets, and so on. So how small can you go? I mean, definitely you're limited by the atom itself, but are there other impediments before that? So single-wall carbon nanotube are thinnest crystalline channels available. So what would be the consequences of that? And this is a very congested slide, so I'll give you the bottom line. The bottom line is that no quantum effects appear, as if just by touching the channel, you create another mechanism that affects the transistor operation. So namely, the contact itself is part of the channel, and this is quantum mechanics at best. So the good news is that this effect may be utilized for a new class of optoelectronic transistor, and we can make those. So how about other effects? Can we paint wall with this stuff? Well, perhaps, but before that, you need to functionalize it, meaning that you have to coat it, and we can coat it such that the carbon nanotube will have positively charged and negatively charged, and this is how it looks. It is coated with polymer, and we can make good junctions, diodes, PN junctions. But before my colleagues in the semiconductor industry start to get alarmed, we try to direct those applications into protecting metals from corrosion. And this is an interesting aspect of it. If you put a diode, the positive side's close to the metal, that's the green layer, and the negative doped material on top of that, well, the surface of the metal stays clean as is. Whereas if you reverse the order, rusty points start to appear. So how about thermoelectricity? In other words, align those carbon nanotubes, heat one side, cool the other, and generate energy. How about opal? You know that butterfly color, the color of the wing of butterfly doesn't come from dyes. It comes from small nano bumps on the wings of the butterfly. And that's how opal, the precious gem, is actually work. And we do it here at NJIT by assembling colloids of glass, basically glass beads, and we grow carbon nanotubes, as you can see, the whiskers. Looks like my hair. In between. And we can do the reverse, like air bubbles, which are very colorful. And then we can imagine PN junctions in the form of dots arranged in some funny way, which are good for nonlinear optics and so on. So what is nano all about? It's about painstakingly rebuilding our world, one molecule at a time, and hopefully for a better environment to live in. Thank you.
What an interesting subject for sure, and I'm sure also that many of you have questions that you'd like to ask, and we have a terrific environment in which to do that. So we're going to adjourn this group down to the University Club and have a little more informal gathering where we can talk amongst ourselves. So let's move on. Thank you.